Swayam Prabha. Digital India. Educated India.
Okay, hello everyone. Today we will start with a discussion on a special type of subgroups called normal subgroups. So, if you have a subgroup of a group G, so you have G and you have a subgroup H, we know that there are left cosets, we have defined left cosets. So, in general the left cosets are different from the right cosets. So, GH, the set of such left cosets where G belongs to G, this may be different from the right cosets HG where G belongs to G, and they may look like, the right cosets may look like these, quite different. The H is the same, the one coset H is also a coset, that is same, but the other cosets may be quite different. Normal subgroups, so this H is called a normal subgroup if these left cosets and the right cosets are the same. So, in other words, if H is a subgroup such that this G H is same as H G for all G in G, then this subgroup is called a normal subgroup, in which case the left cosets and the right cosets will be the same. So, that is because this left coset of G is this and right coset of G is this. So, for every element the left coset and the right coset is the same, which means all the left cosets and right cosets are the same. And another way of writing this is to say that this is G H G inverse is same as H for all G. This is if and only if. Okay, and how is this set defined? It is the usual definition. It is the set of G H G inverse where H belongs to capital H. Now, for a normal subgroup, we can define something called quotient group. Quotient group of H. So, H is a normal subgroup of G, then we define the quotient group. This is first of all the set of all cosets. Now, we do not have to say left coset or right coset, because left cosets are the same as the right cosets. So, we are writing it here as left cosets, but we could have written it as set of right cosets also, it is the same thing. Now, this is the set. Now, what is the operation? The operation between two such cosets is defined as, so if you take two cosets G H then and G prime H, the operation between them is defined as G G prime H. Now, again because these are defined, this operation is defined in terms of two coset representatives of these cosets, we have to show that this is well defined. That is, that if we take different coset representatives from the same cosets, then the right hand side will be the same, okay, it will not change. So, let us do that. So, let us say we take an element here and we take an element here, and an element in GH is of the form G small h. So, you could have written GH as this G small h times h and this as G prime H prime of H. Now, what is the operation between them? Operation between them would be, according to this definition, it is G H G prime H prime times H. Now, we have to show that G G prime H is the same as this. So, let us see this G H G prime H prime H. So, this is a left coset, also a right coset. So, when can we say that these two left cosets are the same, G G prime H, these two left cosets are the same? It is if and only if. So, we know that the two elements, two cosets are the same if and only if these two are in the same coset, which means that this is in this coset and this is in this coset. G G prime is this coset. Either of them, if we prove, this will be proved. So, let us look at G H G prime H prime. We will show that this belongs to this coset. Then its coset, the coset of this will be the same as the coset of this. So, this so we can write this. First of all, let us see this coset itself. So, what do we know? We know that this is H prime belongs to H. So, if you take the coset of H prime, it is the same as H itself, okay, because H prime is there in H. So, it is same as G H G prime times H. Now, we know that the left cosets and the right cosets are the same because H is normal. So, we have G H. Now, this G prime H can be replaced by H G prime, and then this H here, this is same as H. So, G H G prime, and then we can again write that this right coset is same as the left coset, which is G G prime H. Okay. Now, we have written set notation throughout. We have proved as set these equalities hold. You could have also seen that any element here belongs to this. That could have been also proved in a similar manner. G H G prime H prime, any element here is of the form this, take an element from H, let us call it H double prime this. So, we have to show that this belongs to this. Now, to show this, again one can see that this is in H. So, G prime H is an element in the left coset of G prime. So, because the left coset and the right coset are the same, there is an element in H for which this is same as H triple prime times G prime. So, you can replace this by G H H triple prime G prime and so on. So, this is in H again, and you can find another H for which it will, you can put it on the right hand side. So, you could have proved this by taking an element as well. Now, what we have done is that we have defined this group, quotient group, where the elements are the left cosets or the right cosets, the cosets of H, and we have defined an operation, and one can check that this is indeed a group, the inverse of an element in particular. So, what is the identity element here? The identity element E G by H is actually the coset H. H is the subgroup. So, it is its own coset, and that is the identity element. Now, because you can see H is same as E H times H, and so this operation will give you G H times H is equal to G times H again. And what is the inverse? G H inverse is, the inverse of this coset is G inverse H. So, again you can multiply G H with G inverse H here and see that it will give us H. So, this is the quotient group. And so the normal subgroups are interesting, especially for this reason that this quotient group is defined, and it appears normal subgroups also appear in the context of homomorphism that we will see in a moment. So, let us go to group homomorphism. Group homomorphism. So, this is like linear maps between two vector spaces. So, if we have two groups G and H, then and we have a map F from G to H, then F is said to be a group homomorphism if F of G G prime is same as F of G prime for all G comma G prime in G. Let us see some examples. First of all, a map which takes all G to E, the identity element on the right hand side. This is clearly a group homomorphism. This is a trivial group homomorphism. All the elements go to one element E in H. Now, you can take a homomorphism of from G to G where it is the identity homomorphism. So, phi of G is G itself. This is also clearly a group homomorphism. Now, let us take the group R, the group of real numbers under addition, and note that R star, which is the set of real numbers. So, this is the set of real numbers minus the 0 element, and the operation is multiplication. Under multiplication. So, this is a group under multiplication, set of all non-zero real numbers is a group under multiplication, and let us take this map where x goes to 2 power x. What is the image of this map? Clearly, all the positive real numbers is the image of this map, because the graph of this function is like this. So, all these positive real numbers are in the image excluding 0, and one can see that because of the property that x 2 power x plus y is same as 2 power x times 2 power y, because of this property this map is a homomorphism, group homomorphism. Now, let us take this map from Z to Z. This is a group, Z is a group under addition, and we take any integer, it goes to n plus n, that is 2n. You can take addition any finite number of times, let us say 5n, and that is also a group homomorphism. And the image of this map is the set of all multiples of 2, that is 2z. This is the image. Let us take this map of from the integers to integers, and let us take a particular number, let us say 5, and this map is n mod 5, which means the remainder of n when you divide it by 5. Okay. So, this is also a group homomorphism. It is easy to check, and we have in fact studied properties like this, that when you take n1 plus n2, its remainder is same as n1 So, sorry, this is n actually Z5, Z5, right. So, where the addition itself is modulo 5. So, when you take n1 mod 5 and n2 mod 5, their modulo 5 addition is the remainder of n1 plus n2 when divided by 5. Now, let us take another map, fix any element G in G and define this map. Define this map using psi G, and how is it defined? It takes, so it takes any H to G H G inverse. It is easy to check again that is a group homomorphism, because you take H1 H2, what does it give? It gives G H1 H2 G inverse, which can be written as G H1 G inverse times G H2 G inverse, because G inverse G is identity element, and so we have psi G of H1 times psi G of H2. This part is psi G of H2, this part is psi G of H1. So, this is a group homomorphism. Now, we prove a simple property that if phi is a group homomorphism from G to H, a group homomorphism then phi of EG is EH. This is one, and the second property is that phi of G inverse is phi of G inverse. So, let us prove these two simple properties. So, let us just take phi is 1, phi of EG. Now, EG can be written as EG times EG, and then because phi is a group homomorphism, we can break this into phi of EG times phi of EG, and now if you observe phi of this left hand side can be written as phi of EG times EH, and this side has phi of EG times phi of EG. So, it gives us that EH is equal to phi of, by cancellation law, phi of EG. So, that proves the first property. The second property is also very simple. It is phi of, we have just now seen this. Now, EG can be written for any G, we can write EG as G G inverse. Now, this is same as phi of G times phi of G inverse. Now, you can see this relation, EH is equal to this, and this implies that this is the inverse of, this is the these are inverse of each other. So, phi of G inverse is phi G inverse. So, this proves these properties. Now, we define for any group homomorphisms, we define the kernel of the group homomorphism as the set of all G for which phi of G is EH. So, we have this G and we have this H. There is a map which is group homomorphism, which means a certain nice structure in the map. There is this special element EG here, it will always go to this EH. For any group homomorphism, this identity element must go to the identity element on the other side. That is what this is, this we have proved, but there may be more elements that go to this set. The set of elements which go to this EH is defined as the kernel of that map. Now, image of phi is like image of any map, it is the set of all phi of G where G belongs to G. Now, we show this another important result, that if we have phi a group homomorphism, then kernel of phi is a subgroup of G and the image of phi is a subgroup of H. So, let us prove this. First of all, the kernel is non-empty set. It is a kernel is a non-empty set. Kernel is non-empty. It is a subset of G which is non-empty. So, all we need to prove to show that this is a subgroup is that you take any G prime in the kernel. Let's take G and H. G H in kernel of phi. We need to show that G H inverse is also in phi. So, what is phi of G H inverse? This is phi of G, phi of H inverse, because it is a group homomorphism, and we know that phi H inverse is same as phi H inverse. Now, what is phi G? Because G is in the kernel, phi G is identity element. Similarly, phi H is identity element. So, this is identity element in H, EH, right. So, this means that G H inverse is in the kernel of phi. Now, one can also show that this image is a subgroup. So, you take any two elements in the image. So, what they are of the form phi G and phi H in the image. So, first of all, image is again non-empty because EH belongs to the image. And so, you take any two elements and we show that phi G, phi H inverse is in the image, but this is very obvious from this same routine proof here, that phi G, phi H inverse, and then because phi is a group homomorphism, this can be written as this, and clearly this is in the image. Right. So, image of phi is a subgroup. We have seen that for any group homomorphism phi from G to H, the kernel of phi is a subgroup of G. We have also seen that the image of phi is a subgroup of H. Now, we will show that this kernel is actually a normal subgroup. So, we can define quotient group of it. So, here is the result. It says that for a given group homomorphism like this, kernel of phi is a normal subgroup of G. So, we will show that. So, what does normal subgroup mean? It means that left cosets and right cosets are the same, and an alternate way of saying the same thing is to say that take any A in G, then A times kernel of phi A inverse is same as kernel of phi. Okay. So, this is equivalent to saying that A kernel of phi is same as kernel of phi times A. So, we will show that this is a subset of this, and so for first we will show that. So, take any G, take any H, let us say take any G in kernel of phi. So, we will first see that A G A inverse is also in the kernel. to do that, we take the function phi and using group homomorphism definition, we see that it is phi a, phi g, phi a inverse, which is same as phi a inverse. Now, g is in the kernel, so phi g is E. So, we get this phi a times phi a inverse, which is EH, which means that A G A inverse is in kernel, right. So, this proves that A kernel phi A inverse is a subset of the kernel of phi. Similarly, one can also see that this kernel is a subset here, because you take any element in the kernel G, then say let us say G in the is in the kernel of phi, then we know that A inverse G A, we said here that A G A inverse is in the kernel, but you take A inverse G A, this is also in the kernel by just replacing A by A inverse here. So, this is also kernel of phi here. So, what it means is that G belongs to, you take this A to the right hand side, A inverse to the right hand side by pre-multiplying by A and post-multiplying by multiplying by A inverse, we get G belongs to A kernel phi A inverse. So, this implies that the kernel, this subset kernel is a subset of A kernel phi A inverse, okay, here. So, this has so here what we have proved is that we have proved this property, okay, which means kernel phi is a normal subgroup. Now, once we have a normal subgroup, we can define the quotient group, which is G by kernel phi, which are the cosets of kernel phi, and the operation is well defined for if it is a normal subgroup, because this is a normal subgroup. Now, let us observe what happens. So, if you take a coset of kernel phi, you can write it as left coset or right coset, does not matter. So, kernel phi G times this. So, all these elements, the elements here are of the form G H, or let us say G prime, where G prime is in the kernel. Then the phi of that. So, any element here you take, the phi of this is phi G times phi G prime, which is identity element, right, phi G prime, and this is E H. So, it is equal to phi G. So, you see that all these elements in this one coset go to the same image, same element on the right hand side. So, pictorially you can visualize this as that any group homomorphism has this nice structure, that there is a kernel here. So, there is a phi group homomorphism, and kernel contains the identity element E G. This kernel goes to the special element, the identity element here E H, and so all these elements go to the same E H, right, and take any coset of it, that whole coset goes to another single element here. Right. So, and so coset wise there is a collapse, of this whole coset into a single element. You take another coset, that goes to another element, the whole coset goes to another element. So, all these different cosets of the kernel get collapsed into a single element in the image. That is how the a group homomorphism structure is. Now, and these cosets have one-to-one correspondence. In the case of finite subgroup, if the kernel is a finite subgroup, all these cosets will have the same number of elements. So, so this also defines a map, this visualization also defines a map of so let me state it like this. If this is a normal subgroup, not only kernel, actually for a given, so for a kernel, for a given map there are these cosets which then this kernel is a normal subgroup, and this defines a mapping of the cosets, the quotient group. So, these cosets form a quotient group G by H. And so, this is basically the phi group homomorphism defines a homomorphism of the quotient group from the quotient group to G, because every coset goes to a single element, and one can check that this mapping, because phi is a group homomorphism, this mapping when phi is viewed as a mapping from the quotient group to H, this is also a group homomorphism. So, on the other hand, if you are given any normal subgroup, we can define a mapping from G to G by H, where we basically collapse every coset of H into that, we visualize it as an element in the quotient group. That is all this mapping is. So, G goes to G H, okay, and the kernel of this map is H itself. Okay. So, this is a group homomorphism. This is a group homomorphism. Now, as I said, so this is for a given subgroup, one can see that one can define a natural map, a canonical map from G to the quotient group. Now, using this canonical map, so this is basically visualizing the cosets as elements in the quotient group. Now, we can define, you can take any given any group homomorphism phi of from G to H, one can see that there is a map here G to H. There is a kernel, phi is given, so we have kernel, and so we can see that there is a quotient group this, and this phi basically defines a group homomorphism here from the quotient group of the kernel to H. Okay. Now, what is this map? This map is the canonical homomorphism that we discussed just now. So, for kernel there is a, so this map is basically visualizing the elements. So, taking the elements of G to their respective cosets. Okay. So, there is a collapse happening, collapse of the whole coset into a single element, whole coset being viewed as a single element in the quotient group. Now, that collapse was being done by phi here, but now we are saying that phi can be broken into two parts. It can be visualized as composition of two group homomorphisms. One which first collapses the cosets into single elements and visualizes them as elements in the group quotient group, elements in the quotient group, and then for those elements there is a map that takes it to the image of phi. So, this map let us denote by phi bar. Okay. So, given any group homomorphism, there exists a phi bar from this quotient group to H, such that we say that this diagram, the diagram commutes. What it means is that there are two ways to go from G to H, this way and this way, two paths, and both paths lead to the same mapping, which means that is phi is same as phi bar composition psi kernel F, where there exists phi bar which is 1 to 1. Okay. That is, it is injective group homomorphism. Injective group homomorphism such that the diagram commutes. Now, the proof of this is quite simple, but most importantly this visualization is important. What we are saying is that we are breaking phi into two steps. We are saying to do the operation phi, we can think of first associating every element G here to its coset. First collapse all the elements in the coset into a single entity, which is an element in the quotient group, and then that coset was being taken by phi to one element here, and that is the mapping from this coset, this element in the quotient group to H. So, that mapping then becomes 1 to 1, because the whole coset here which was being taken to a single element by phi is being viewed as a single element in the quotient group. That is the important thing. So, now the proof is by construction of phi bar. So, we can define phi bar. How do we define? So, we take any coset of the kernel and define it, it is of this form G times kernel F, and we define it as phi of G. Okay. Now, we need to check if this is well defined, because this definition is in terms of a coset representative. Changing the coset representative should not change the definition. So, any element in this coset is of the form G times H, where let us not write it as H, G times G prime, where G prime is in the kernel. So, if we take this and call this G prime times kernel F, then what is phi G prime? That should be same as phi G, because phi G times phi of G prime, and this is the identity element. So, it is phi of G. This is the, so as a result, it does not matter what coset representative here you have taken here, whichever you take from this coset, it gives you the same image for phi bar. So, this is well defined. Now, this is well defined. Now, it is group it is a group homomorphism. This is clear, because it is easy to check that phi bar of G kernel F, two cosets, you take two cosets G prime kernel F, and what is the operation between two sets? We have defined this as G prime times kernel F, and then this is phi of G prime, which is same as phi of G times phi of G prime, which is also same as phi bar of G kernel F times phi bar of G prime kernel F. So, we see that phi bar satisfies the defining property of a group homomorphism. So, it is a group homomorphism. Now, one to oneness can be also easily proved, that you take any two cosets G G prime, G kernel F and G prime kernel F, G kernel F kernel phi sorry, and G prime kernel phi. It should be, I should have written it as kernel phi here, it is not F. And if you take phi bar of this, so 1 to 1, no, not this, 1 to 1. So, you want to say that phi bar of this is same as phi bar of this. Then what does it mean? It means that this is defined as phi of G is equal to phi of G prime, which would mean that that phi of G prime inverse is E h, and that means phi of G prime inverse is E h, that means G prime inverse is in the kernel, and that means G belongs to kernel phi times G prime. That is same as G prime times kernel phi, it does not matter whether you write it as left coset or right coset, because kernel phi is a normal subgroup. So, what you see is that G kernel phi is same as G prime kernel phi. So, if phi bar of G kernel phi is same as phi bar of G prime kernel phi, then these cosets are the same. So, it is a 1 to 1 map. So, phi bar is injective. Okay. And the fact that the diagram commutes, that is this composition relation holds, is clear. Let us see this side phi bar of psi kernel phi of G. We want to show that this is same as phi of G. So, what is this? This is a canonical homomorphism which is phi bar of G kernel phi. And what is the definition of phi bar? It is equal to phi of G. So, this gives us the same image, this composition gives the same image as the image of phi. So, this says that phi bar composition psi kernel is same as phi. Okay. So, that proves the whole result, and this is an important result. It lets us visualize this any group homomorphism as composition of two group homomorphisms. One is a canonical group homomorphism, which lets us view the cosets as the elements of the quotient group, and then there is a 1 to 1 mapping, 1 to 1 group homomorphism or injective group. Now, another small simple result is that if G is a cyclic group and you have a group homomorphism f of f from G to H, then the image of f is also cyclic. Image is a subgroup of H for any group homomorphism. Right. So, the proof is very simple. Basically, we show that that f of A image is generated by f of A. Okay. So, because we know that since G is cyclic, G is the set of all A n where n belongs to Z, and then the image of G is by definition then the image of F image of F is by definition F of A power n this, and this for negative power as well as positive powers using the group homomorphism property is nothing but it is F A power n where n belongs to Z, because F of A inverse is same as F A of F A inverse also. So, for negative powers also this holds. Okay, so, this is this. Now, we will stop today after introducing some notations and basically terminologies which are commonly used. We say that a group homomorphism is a monomorphism if kernel is E g, that is we have not shown this, but we can show that F is injective if and only if this. Now, we have not done this proof, but we can quickly do this. Clearly, if F is injective, then the kernel must be E g, only E g, because two elements cannot go to E g. Two elements cannot go to the same element on the right hand side, which is E h. Now, the other direction, that is if the kernel is E g, then it must be injective. Why? Because if F of G is same as F of G prime, then we see that F of G prime inverse is E h, but F of G prime inverse is same as F of G prime inverse, and then combining with this you get F of G prime inverse is E h, and that means G prime inverse is in the kernel, and but we know, because this is given, this G prime inverse G prime inverse must be the only element in the kernel which is E g, which means G is equal to G prime. So, F is injective if and only if kernel is that. So, for group homomorphism it is easy to check if it is an injective homomorphism or not, just check the kernel. Now, epimorphism means it is a surjective homomorphism, that is image of F is the whole group H. Endomorphism is a group homomorphism from G to G itself. Okay. Isomorphism is a group homomorphism from G to H, which is a one-to-one correspondence, which is bijective, that is bijective group homomorphism. Okay, it is called isomorphism. And when we have an isomorphism between two groups G and H, we say that G and H are isomorphic. Now, this is very important. When two groups are isomorphic, basically it means that the groups are the same, essentially the groups are the same, except for renaming of the elements. This group can be obtained from this group G by renaming the elements. Okay. So, every element in G can be thought of as the corresponding element F of G. okay, so that the operation is also preserved. So the group homomorphism F is not only just to any one to one correspondence, but it is a bijective group homomorphism. So G prime goes to F G prime, then if suppose G and G prime their operation is G G prime here, its image will be the operation between these two F G F G prime. Okay. So, the operation of G G prime, this product will go to the product of F G and F G. So, you are basically thinking of this element being this element here, this element being this element. So, this element being this element, this element being this element. Okay. So, here there is a one to one correspondence under which the group operation also is preserved. So, that is what isomorphism. So, whenever we have two groups which are isomorphic, we think of them as basically the same group. An automorphism is a group homomorphism from G to G which is bijective. So, one can say that it is an isomorphism of G from G to G, or you can say it is a bijective endomorphism. It is a map where G, this both sides are the same group G and G. Okay, thank you.